We know so little about dark matter. Yes, we see some evidences of its existence, but we never had smoking gun proof of the dark matter existence.
As we first reached out to try and understand our place in the universe, what we learned was far stranger than any myth, legend or religion had prepared us for. We learnt that we were not at the centre of everything. Our home is just one tiny rock, orbiting one very ordinary star among hundreds of billions in our galaxy, and trillions upon trillions in the universe. In the last 100 years, we've had another surprise on that scale. We've learnt that the visible universe, that which we can see or detect using light, heat, or radio waves, is not the whole story. To be precise, it's only 15% of the story. We now know, as much as we can know anything, that 85% of the matter that makes up the universe is invisible to us. That's why we call it dark matter.
I'm very excited to be back at CERN. We're above the Large Hadron Collider at the ALICE experiment, and I'm about to meet the coordinator of physics, if he's not too busy. Oh, here he comes. Alexander.
Nice to meet you.
Neil, how are you?
Welcome to CERN.
Thank you very much. Can we go in there?
Unfortunately, right now it's not the best moment because we are running an important test.
You are actually running an experiment?
Absolutely. We are taking data at a very high rate now, but we can go over there and I can show you what's going on inside.
This is a lot more industrial and chunky than some of the other places I've been.
Yes, here the real work happens. Exactly, yes.
So all of these people, do they work full time for the ALICE experiment?
So we are operating the experiment in shifts of 8 hours, and we are a collaboration of 2,000 people. Some people are permanently here, like me, but some really come for a period of 2-3 weeks to operate the experiment in shifts.
And the data that everybody's monitoring and collecting, it flies all over the world.
Absolutely. We first store it here, then we find out the interesting events, and then we distribute it to computer centers all over the world where it gets analyzed by postdocs and PhD students.
When the experiment is running, how many events are you recording?
So right now we are collecting 4 million events per second.
How can you analyze that much data? 4 million events per second.
Well, we have a lot of computers all around the world which are assembled in the so-called LHC computing grid, and we have like 100,000 CPUs, okay, and each of them analyzes one event in less than a second. So imagine the fascination I have every day when I think of these physics processes that happen inside the collision.
Yeah, I know, but I can't compute it. I can't deal with it.
The actual collisions are happening below us,
right,
around 50 meters. Right now we cannot go down because the radiation level is too high. You see the access door is now closed.
If it wasn't running, we could go in there.
We could go in there right here. But since it's running, we can only go to the right above the collision point.
So that's the detector down there?
Absolutely. Below these concrete blocks is the detector, and that is where the collisioning are happening also right now.
Why is it covered in this concrete?
We have installed this concrete in order to shield the radiation.
And it's very noisy in here. Why is this?
So we have to permanently ventilate the cavern because some of our detectors operate with flammable gases, and if there's a small leak, these flammable gases should not accumulate. And that's why you hear this noisy ventilation.
Continuing our discussion in the quiet of the outdoors seemed more profitable, and it also helps us with a visual aid.
You were right, it is quieter here. And I want to compliment you on your mural. You have the best mural at CERN.
Thanks for the compliment. It's a one-to-one sketch of our detector.
One-to-one?
Yes.
That's actually what I was looking down on.
Exactly. That is below the concrete you would see this, in fact.
So what was the ALICE detector designed to do?
ALICE is designed to investigate the quark-gluon plasma.
Sorry, you're going to have to back up a bit. What's a quark?
A quark is the fundamental constituent of matter. So you have heard of atoms. Atoms are consisting of electrons and of protons and neutrons in their core. Protons and neutrons itself are consisting of 3 quarks. And what we are doing here is to investigate a new phase of matter in which these quarks are not bound into protons and neutrons anymore, but they can roam freely and interact freely with each other.
So what's a gluon?
The gluon is the exchange particle for the strong force which intermediates the force between the quarks. It's similar to a photon which intermediates the force, the electromagnetic force. The gluon intermediates the strong force.
It's no accident that it's called a gluon.
Absolutely. It comes from the word glue because it glues essentially the quarks together so that they bind into protons. But at the extreme temperatures which we reach here, we can free them so that they are not bound anymore in protons and neutrons.
Why do we need to know about a quark-gluon plasma?
It's interesting because the universe, few microseconds after the Big Bang, went through the same phase. And we want to essentially validate our picture of the, say, first seconds of the universe by recreating these conditions in experiments under controlled conditions.
So you're actually taking a snapshot of the birth of the universe.
Exactly. So we often, what we do, call the mini Big Bang, essentially. So that, of course, the Big Bang was a huge event, but it happened only once. But we can restage many small Big Bangs in our experiment down here.
4 million times per second.
4 million times a second.
So let me see if I understand this. At the beginning of time, the Big Bang formed this quark-gluon plasma, and it cooled and formed all the matter that now makes up the universe.
Precisely. And we are now doing the inverse process. We are essentially reheating the matter and create the quark-gluon plasma again, then it cools down again and we see matter again.
But you're colliding something a bit different here than most of the other experiments, aren't you?
Exactly. So we are colliding lead ions, and we do this once per year, actually 1 month per year at the LHC. Normally we collide protons like right now, but in September, October, November, we always take 1 month to collide lead ions.
Usually streams of single protons or hydrogen ions are collided. But lead is a much heavier element with 82 protons and between 122 and 126 neutrons. The variant with 126 neutrons, lead-208, is the one used here.
So I'm guessing lead being so heavy, you're creating more energy when you collide a lead ion.
Exactly, you have more energy and you produce many more particles. So in a normal LHC collision, you produce like 10 new particles, while in a lead collision you produce 2,000 of them. And in order to record them all, our detector is much more granular than the other experiments.
Some of the particles that Alice found were particularly interesting, like the antimatter equivalent of helium. It's extremely rare on Earth, but the collisions in Alice have produced thousands of anti-helium nuclei.
You collided this lead and you got a surprise, didn't you? You found anti-helium.
Yes, even though we were not originally designed for that, we found out that thanks to the many collisions we investigate and the high energy, we produce a rare species of particles, so-called anti-helium, which could also originate from dark matter decays. And by measuring them in our detector, we can provide input for the search for them in the universe with satellite experiments. And like this, we can contribute to dark matter. And what we found is that, what is very difficult to investigate is how these anti-helium particles interact with matter, because they are antimatter, they usually immediately annihilate. And this annihilation probability was not well determined. And we were able to measure it. And we could find that anti-helium that can be created in dark matter interactions in the center of our galaxy, it annihilates not so often so that it can very well reach Earth. And this was our main finding last year.
I'm really struggling with that. How does what you do here inform what's happening out in the galaxy?
So you have to imagine the galaxy is of course enormously large, but it's not empty. So while you have in air, you have millions and millions of atoms. In the universe, you have only 1 atom per cubic centimeter. Now, what could happen with an anti-helium particle that is created by dark matter in the center of the galaxy, it could interact with this 1 atom because it travels 10,000s of light years until it reaches Earth. So we needed to know how probable it is when these 2 particles meet that they annihilate each other. And this we could restage in our experiment You create antihelium in the center of the detector, and then you measure how many arrive at the outside of the detector at 3.5 meters where the detector ends. And while crossing this amount of material, it's roughly as much material as you have between the center of the galaxy and the Earth.
Because there's so much more material in the collider, the journey that the antihelium makes in the collider is the same as the journey it makes from the center of the galaxy.
Precisely.
Because there's so little material in the rest of the galaxy.
Absolutely.
I think I may actually understand it now.
Perfect.
But where is your heart? Are you a quark-gluon plasma guy or are you a dark matter guy?
I'm a 50-50 person, so I like to investigate both. And over the years, we have done many things which we were never thought we would do when we designed it. So, and that is for me the exciting part of my job.
The ALICE experiment, based on the Large Hadron Collider, is a multi-purpose detector originally designed to investigate the state of matter that existed immediately after the Big Bang, known as the quark-gluon plasma. But in recent years, ALICE has also begun to contribute to the ongoing and worldwide search for direct evidence of dark matter. Dr. Ivan Vorobyev is a senior researcher.
Thank you very much.
Oh, so this is the exhibition.
Right. Welcome to the ALICE exhibition.
Oh, wonderful.
The point 2.
What do we have here?
This is the actual inner tracking system, not a mock-up, which was in operation since 2010 up until 2018. What you see here is the core of the ALICE experiment. It's the detector located closest to the interaction point.
And there, what I see is a pipe in there. That's actually where the beams met.
Exactly. So collisions of protons and heavy ions from the LHC, they happen right in the middle of this tube, which represents the beam pipe. It's part of the LHC and it's under vacuum. And this apparatus sees the collisions first, so to say. You see a lot of cables, wires, data acquisition, power supply, cooling. So even this machine needs a lot of efforts to be operated. It is exposed to the enormous radiation, as you can imagine, because it's the detector closest to the interaction point. And yeah, it's a beautiful camera with millions of pixels sending us the data from the very, very closest point to the interaction.
When you're creating that mini Big Bang, what are you actually looking for?
We cannot see the quark-gluon plasma directly because it lives only for tiny fraction of a second. We talk about 10 to the minus 22 seconds. But we can study its properties by looking at how many particles were produced, which kind of particles were produced, in which way they were produced, in which direction, how they interact with each other.
Let me get this straight. When you say 10 to the minus 22 seconds, that's 1 divided by a 1 followed by 22 zeros. Have I got that right?
Exactly. That's a very short amount of time, and we need ultra high speed camera to capture every single detail of this very short amount of time.
When I tell people that I'm coming to a place like this, and I try to explain to them what it is we're going to be making a film about, and that they say, why? Why do we need to know that?
I would say that this is what made us humans. Trying to understand the universe around us, we went to 2 different directions, one can say. One, building larger and larger telescopes, looking at the stars, the galaxies around us, trying to understand the universe on a larger scale. And the other way was to go to the smaller and smaller details, trying to break up atoms, nucleons, to see what is inside. And that's exactly where we went with the machines like the LHC. Right now, we reconstruct 500,000 proton-proton collisions every second.
So you've been doing those 500,000 collisions a second for many years. Why do you need that much data?
We need to analyze a lot of data because some phenomena happen really very rarely and they might be really very interesting.
One of those rare phenomena was the production of antihelium, which Dr. Kalweit mentioned earlier. As he said, it's theorized that these particles may be created when dark matter particles collide near the center of our galaxy. They go on to travel throughout the rest of the galaxy.
What makes you think that these particles are also produced by dark matter collisions?
This is pure theory at the moment, but we believe that if this is the case, if dark matter is some kind of particle which interacts with the standard model particles and then can produce standard model particles, we see that it's actually very easy for dark matter to produce those anti-nuclei at the low energy, so produce slow anti-nuclei which will fly in the universe and might even end up in one of the detectors near Earth. So if we catch slow, low energy anti-nucleus like anti-neutron or anti-helium, that might be a very, very, very good indication for something new, some new physics, possibly dark matter.
Another detector looking for that indication is the AMS, or Alpha Magnetic Spectrometer, an experiment that is the brainchild of Nobel Prize-winning Chinese American physicist Professor Samuel Ting. AMS was attached to the International Space Station in 2011. Put as simply as possible, the theory behind AMS is that if you can find more of certain particles, such as anti-helium, in near-Earth space than is predicted by the standard model of particle physics, then it could be an indicator of dark matter.
One thing I need to help you with, we're always saying compared to the standard model tells us. What is the standard model?
Standard model is a theory which currently comprises our best knowledge about the particle physics. It has, it incorporates three fundamental interactions we know at the moment. It is not ideal, it's not perfect, it doesn't have gravity inside, for example. It doesn't explain few phenomena we have seen with many experiments, but it's currently our best knowledge of the particle physics.
So we know that dark matter exists through inference of galaxies and cosmic lensing. So there's a whole invisible part of the universe which is not explained by the standard model.
That's true. In the standard model, if you stay within the standard model, there is no good explanation for phenomena we explain currently with dark matter. But we believe that the standard model might be just a piece of a more complex theory which would incorporate effects like dark matter, also gravity, the theory of everything.
So I think I'm starting to get it. So what you're saying is we think the standard model will produce this much anti-helium, anti-deuteron. So if in space they find more than that, that's an indication.
Exactly, you are completely right. So these processes of collision between the cosmic rays and interstellar medium, this is a standard model process. And this is exactly what we can study in ALICE in details. And if we see, so these models, we can properly calculate the probability of anti-helium to be produced in such collisions. But if we see with the experiments flying around the Earth that the amount of antimatter we catch is much more than what you would expect from the standard model processes in the universe, that's definitely indication for something new, some physics beyond the standard model.
Which could be dark matter. But once again, you know, we kind of know that dark matter exists because of the way galaxies behave, cosmic lensing. Why do we need to spend billions of pounds, dollars or euros trying to track down exactly what it is?
Dark matter comprises about 85% of the mass in our universe. We don't know 85% of the mass of our universe. We know so little about dark matter. Yes, we see some evidences of its existence, but we never seen it directly. We never had smoking gun proof of the dark matter existence, that we need to look everywhere. We need to do direct searches at the LHC or other experiments. We have to look into the space for anti-nuclei flying around our Earth. The more we look into this, the closer we get to this question, what is dark matter?
You're a young man.
Thank you.
You're welcome. Will you ever be standing at the front of the podium where we're going to be this afternoon and saying, we've found it, we've got dark matter?
I hope so, but it's not, of course, given for free. If we don't find dark matter in the next decades, this will not be for lack of trying, that's for sure. We will do our best to find it, to understand it, but I'm pretty sure even the path to look for dark matter will be interesting than the actual final result.
The journey is long.
The journey is long and it will be interesting in any case.
We were very fortunate that the day we were filming at the ALICE experiment was also the day that Professor Ting, the creator and director of the AMS experiment, was giving his second results seminar. We were not allowed to report on the proceedings, but we could speak with Alexander and Ivan afterwards. So we've just been to a seminar about the AMS results from Professor Ting. What did we learn?
They've been collecting data now for several years, and he showed the latest results. And I mean, the thing we are most interested in, he showed at the very end, the antimatter results. They confirmed that they see some candidates, but they are not absolutely sure what it exactly is. Is it signal or is it background? But hopefully soon they will come up with a definitive answer on that.
The candidate that he mentioned was the anti-helium, the one you were telling me about today.
Exactly.
Absolutely.
So they see at least reliably one anti-helium-4 event, and as Professor Ting said, it is extremely difficult to explain this even single anti-helium-4 event with the physics we know so far. So this is why I think it's also the reason why they are very, very careful about publishing these results in a scientific journal, because even the confirmation of one single anti-helium-4 event in the AMS will mean a breakthrough in physics.
So I didn't understand, it's only one event that showed us that exciting data?
He showed the example of one event, probably the cleanest they have, and he mentioned that there are a couple of them. So yeah, we have to just now wait and see. I mean, they have to understand their data better to see if it's really one of the exciting anti-helium we are looking for, or if it was a detector effect.
And how long will that take before we know whether it is the exciting one we're looking for?
So that no one can tell. It depends also on how fast their analysis goes. He mentioned today that they will have a significant better understanding within the next 5 years.
So one more step on the long journey to find dark matter.
Absolutely.
Yes, yeah. The good news for today is that, I mean, they see these candidates now since a couple of years, but they have so far never said that they found out that it's background. So the hope is absolutely higher than before.
So when you told me about this, when we were talking about the seminar, you told me not to get too excited, but this is exciting, isn't it?
It was a very exciting day, yes. Yeah. I mean, you see these seminars are given every 5 years, essentially, and I mean, today you were here, and it was a nice coincidence. And I don't know if you noticed, I was very nervous during the talk, especially
I did notice
because
that.
the antimatter part came at the very end, and yeah, I'm happy to see that they still have their candidates, that they still continue to search, and that we expect an update from them within the next 5-6 years.
Ivan warned me to wait, that it would come at the very end.
Yeah.
Exactly.
Yes.
One thing we should keep in mind while talking about this possible anti-helium events in the IMS is that, as Professor Ting said, IMS is a unique experiment flying around Earth on the International Space Station. So there is no possible way to cross-check these results with another experiment, not in the nearest 10-20 years. So that they have to be absolutely sure about these results, because we cannot cross-check them with the other similar experiments.
So it sounds like it's time to send another AMS detector up into space.
There are plans for an even bigger version of the detector AMS, and that will be something probably for the 2030s, 40s, and hopefully this will also become a reality. Yeah.
Yeah, these future experiments, they might supersede the results of the IMS we've seen right now, collected over 10 years in 1 month's time.
Well, thank you for allowing us to be with you today, and especially on this day where the news just got a little more exciting, and being our guides. Thank you very much.
Thanks to you.
Thank you very much.
It was a pleasure.
It was a pleasure.
But of course, for these men, the real pleasure will be when they can find direct evidence of dark matter.